let's get started. So I do want to point out 1 week from today, we will have our first exam. It'll be in this. I think I looked at the old exams and they were a combination of multiple choice and short answer, where a majority of the. I'm not gonna make it like Scantron, but you're welcome to bring a pen or pencil, but you will need a calculator. And I prefer pencil, but I'm never gonna turn away a pen. So yeah, it'll be, I would say probably about 30 to 34 multiple choice. And I think that if you look online, I'm pretty sure I published, you can see the fall 2024 exams. It's under the first module. And you can see how those questions are structured. And then I do plan on the Wednesday before the exam, we finish everything. We're gonna do review. I printed those out. I have those questions ready to come in and do those questions with you. So I can answer those questions with you. And then also the exam will not take up the entire class period. So I plan on maybe doing more review before the exam starts and then do the exam once I'm ready. So my goal is to give you a 50-minute exam. Maybe I'll start a little bit early to give you some more time. But that'll be next Friday. Before next Friday, just reminder, all of your homeworks need to be submitted. I have one more homework I need to create. That'll be 1.6, 1.7, and then you have 2 quizzes out. Well, for 1 quiz out, I'll have the second one out today, and those need to be completed before the exam. I know that I have 2 drops on those homeworks and 2 drops on those quizzes. Please don't let it be the first ones, because those are the easier ones. Any questions on that? Okay, awesome. Today, we're gonna do letter math in the first half, and I have a fun little activity to do, well, fun subjective. I think it's fun. It's okay if you don't. We'll have a activity to do, and then second half, we'll do unit conversions. The unit conversions will require calculators, so just make sure you have your calculator out ready for the second half. Okay, so let's talk letter math. The goal is to develop a problem-solving procedure that will naturally expand to accommodate any math equation you apply to chemistry. In chemistry, a lot of our one in general chemistry too. Obviously, I'm not going to expect you to have those memorized, but I can throw after this section, I can throw any equation at you that has a bunch of variables and expect you to be able to rearrange it using algebra and solve for something specifically. So even though I don't expect you to be able to use it per se, it's how you rearrange it. That's our goal, is I can throw any type of equation at you and you can rearrange it. And then we're going to hit verse. This is a fun little way of analyzing those types of equations. That's going to be on Monday. So I know it's a part of 1.6, but we'll do that on Monday and then start 1.7 on Monday. So yeah, today's only letter math and unit conversions. So think, pair, share. How do you solve a mathematical equation for a variable? So alternate wording would be isolate a variable, find a variable. Let me add another slide here. I'm gonna pause real quick because I want to kind of do a review with you. Should have done that before class started. All right, I'm coming now. Awesome. Right. So just an overview before I kind of do this practice with you. We're going to solve for or isolate or find a variable by undoing the math operations that tie it up by doing the opposite math until that variable is all by itself. I know it's wordy, but I'll show you what I mean. We're going to rearrange the letters to solve for a variable before substituting materials. And the variable you solve for should appear all by itself without any math operations on the left of the equation or equal sign if in your final answer, and then we're going to mainly do it 1 step at a time. As you see this and get more and more comfortable with it, you might be able to start doing certain things in your head and skip some steps. As long as you know what you're doing and everything is working out, I don't want you skipping those steps until you are truly comfortable and are getting the correct answer. So fundamentals, and then we'll work towards being able to do things in your head. Let's just do a review real quick. This is kind of like what we learned when we first took algebra. A variable is usually a letter or something that's not a number to represent something. So I have X right here to represent variable for, I don't know. If I want to figure out what X is, what's going to be my first step? Yes, so this, I would say general chemistry 1 and 2, and even quant for me, is all out. And even if you haven't taken algebra in decades, we're going to do a lot of review of algebra now. So you might be rusty, but it will come back to you because you've already done it. So for us to isolate X, we need X all by itself on one side of that equal sign. The first thing you have to do is you have to get rid of everything that's next to X or connected to X. And previously I said opposite. So for me to get rid of this +3, I have to subtract 3 on both sides. So 5 minus 3 is 8 equals X. And then since there's nothing else next to X, that's it. That's all I have to do to isolate that here. Sorry, thank you. I'm going a step further because the next one I was going to do is -3. Yes, so X would be 2. If I was to replace this way, -3, that's what I was thinking. For me to do the opposite, I would have to add 3 on both sides. So that would cancel, and now I would have 8 equals X. All right, let me do one step further. I'm gonna keep the same numbers. Might need a calculator for this. What order, I guess not order of operations, what type of math is between the 3 and the X? So how do I get rid of the 3? Divide. So I need to divide by 3 on both sides, so those 3's cancel, and X equals 5/3, or let me just do it real quick. $1.6667. I think that's just 1 2/3. But yeah, so you would just do the opposite. And if I was to then do 5 equals X/3, how would I get rid of the 3? Multiply both sides. Those 3's will cancel, and now I have 15 equals X. Okay. So that's just basic. We're gonna be doing this over and over and over again. But the gist is always gonna be the same. If I have multiplication between the variable I'm looking for, you'll divide to get rid of it. If I have division, you have to go the other way around. Let me do a fun one. Well, that's, like I said, it's subjective. Ignore me. If you disagree with me, I'm not gonna say you're wrong. So if I have 5 equals 3x plus 2. This is when we have to think about order of operations. You don't want to start inside of the parentheses just yet because the 3 matter. What do I do about this 3? Distribute. So I could definitely distribute this. I believe it also works out if I just divide by 3, but let's distribute. So 5 equals 3x, and don't forget, when you say distribute, it goes into both. 3 times 2 is 6. Okay, a little bit better. Next, what I do? -6. So 6 cancels. I have -1 equals 3x. Next step, divide by 3. So that's -1/3. Or 0.333. I'm curious, if I took the 5 and divide, if I just didn't distribute, let me check and see if I could do that. 5 divided by 3. -2. Yeah, so that was one way. If you distribute as one way, you'll get the correct answer. You could also do it this way too. So both ways are correct. You need to do what's best for yourself, and you're not incorrect if you pick. So if you just divide by 3 on both sides, so I get 5, I'm gonna skip a step, equals X plus 2 minus 2. X equals -0.33, same answer. So both methods work. You just pick what works best for you. Sure, I'm not missing any. Right. Dr. Patterson is a huge Trekkie. She also likes Dune a lot, so you might see some of these in there. So sage advice from Captain Picard, one impossible thing at a time. So I know that we had one variable on those last problems, but when I start introducing more than one, just take it one step at a time, especially if you're overwhelmed. As you get more comfortable, you can start skipping steps. I do it all the time because I love algebra and it's just what I'm good at. And I have to remind myself, okay, let me go back and do it one step at a time to just double check and make sure I'm doing it right. So tackle one operation, addition, subtraction, or multiplication, division at a time. And there are always options. This is why I love chemistry. There's always a way to figure out the answer. There's never just one way to do it. It's not a memorization base. If you don't got it, you can't answer it. I like to call it bullshitting. I know there are other more nice ways of saying it, but there's always a way to answer. There's always options. So there's many paths to the right answer. Just make sure you're using legal math. Okay. Some students will try to skip steps because they're on it, but they just miss that one algebraic thing, and that prevents them from getting the right answer. Let's now practice. So this ideal gas law equation, I'm not going to have you like throw in numbers. The variables mean things. So P is for pressure, V is for volume, N is for moles of substance, R is the ideal gas law, and D is temperature. So with these types of problems, when you hit Gen Chem, I might ask you to figure out the pressure, and I would give you all of the other variables in numbers. So you could do it two ways. You can forward in. So once again, when you hit Gen Chem and you feel like one method is better than the other for you, do what works for you. But for me, this is the best method that works for me, and being comfortable with this will make the next step better. So we want to isolate P. P is on the left-hand side and it's connected to the V. How? So to get rid of the V, I have to divide. So PV equals nRT. So I want P, I'm going to divide by V on both sides. That way those V's cancel. And now if I would solve for pressure by itself, just need to take N, R, and T and divide it by V. And that's it. So you'll be given those numbers, you'll be given those, like what it represents, especially when I think I'm creating a document for Monday that'll be like this, where you move things around and then you plug in what I give you. Any questions on specifically this? Okay. Please don't hesitate to ask. Now let's solve for T. T is on the right-hand side. How is it connected to the other two? Multiplication. Now, I want to point out there are two ways to do this. Previously I mentioned it, taking it one step at a time. We are attached to N and R here, so we need to eventually get rid of both. But if we were to do it one step at a time, I would have to divide by R on both sides, and that way the R cancels. And so I would have NT equals PV divided by R. And then I have to get rid of the N, which is, moving the N down here. So you could break it up into do one step at a time, but I prefer when it's like they have the exact same math, they're all multiplication, just divide by both. So I'm going to erase this. Okay. Divide by N and R. And that way both cancel, and T equals PV over NR. How does that feel? Like, is that okay? Because I just want you to you can definitely break it up and do it by the N and then do it by the R. But when you start getting into it, if it was the same exact type of math between them, you could do it both at the same time. Now, if one was multiplied and one was divided, you'd have to split them up. I think you might hit this in Gen Chem 1. I haven't taught Gen Chem 1 since it's like 2021, so I don't remember. But I definitely hit this for quantitative analysis. So this is an energy equation, energy of a photon. So does anyone know what a photon is? You gonna guess when I say, what about photo? What do you think when I say photo?
Still image.
Still image. So a photon is an individual particle of light. So photo, I think that's where like the photo comes from. So energy, capital E, and I'm not gonna ever, I don't expect you to memorize this. I just expect if I throw any equation at you, can you rearrange it? So E is energy of a photon, H is Planck's constant, C is the speed of light, and the upside down, this is called a gamma, a lowercase gamma. Oh, you're right, it's a lambda. I'm like, gamma, capital is this. Forget what the lowercase gamma, that's definitely a lambda. Sorry, my Greek is not good. So lowercase lambda represents the wavelength. So we typically use wavelengths to describe like colors. I know if you're doing visible spectrum, like wavelengths can be like, okay, this wavelength is for red, this wavelength. So no worries about being able to utilize it quite yet. But if I ever ask you to solve for it, so if it wants me to solve for H, let's do it. So E equals HC over lambda. I can't do H right away because I got to get rid of the lambda first. So what am I going to do first?
Multiply by the
Multiply by the lambda on both sides. That way it cancels. And now I get lambda times E equals HC. That looks so much better for being able to isolate C. If you tried to do this all at once, it would be quite confusing until you get a little bit more comfortable. I wouldn't even do this all at once. I do this in two steps in my head. What's the next step? So I want to get H. Yes, I want to get rid of the C. The C is multiplied. So I need to divide by C on both sides. And go up here. So for me to get A by itself, it's going to be lambda times capital E divided by C. Now, if I was to give you the wavelength, the energy, and the speed of light, you can plug them in directly and so we haven't hit the theory in lecture yet. Yeah, one step at a time. Don't try to shorthand things that have more than one type of math. And then it is if I like took out this dot, but it's the same.
Then we just skip a step and multiply by C over the whatever that's called.
Okay, so if you want to do it in one step, I'll show you, I think. I'm gonna erase it. We're gonna kind of like do this together because I might be wrong, but I'm not gonna ever advocate for y'all to do this in one step. If you're really, really, really good at math, which I don't consider myself amazing, I want H by myself, so that would be C divided by lambda. Okay, if I want to do this in one step, I would say this is multiplication, and I would divide by C divided by lambda on both sides. Okay. So if I did that, by the way, this might be confusing. If it's too confusing, just don't do this. That would be E. And then what happens is, so E divided by C divided by lambda is equal to E divided by C multiplied by lambda because it's a reciprocal. That makes sense. So this, there is nothing here. E divided by C divided by lambda is the same thing as me reversing it and multiplying it by the reciprocal. So lambda, let's see if I can simplify that. Like that. So that's why it would end up being E times lambda divided by C. That's just an extra algebra step when you're dealing with more fractions. Yeah, that's why I'm like, I'm not a fan of doing this. I rather just break it up into 2 steps. Sorry. That was like way out in left field. I'm so sorry, but that's how I would do it in one. But I typically would never do that in one. But that's a great question. I like the, like, thinking of how we could. Are there any other questions on that? So the main thing as you're learning, you're new to this, keep it simple, clean notation, make it easy for you to follow. Sometimes students, I can see the way they're thinking. Let's say we're doing a short answer problem on the exam. I love to see how their brains work and I can see their notes and I can see how they're thinking, but sometimes students just don't. It's not straightforward. So like they'll do something here and then something here. I'm not sure how they got to this. So you want to make sure that you're cleaning up your notes as you go, especially on the exam, because like I can see how like this confused them here and so keep it clean. If you have something here and you're playing around with the math, then underneath it, clean it up, then clean it up. Multiplying means put it in the numerator. So that means if I had, this would be in the numerator. See how it's both on top? It would be the same thing as me dividing it by 1. Dividing means putting in the denominator. So 3 equals 5x. Now the 5's in the denominator. It's underneath. So numerator is on top, denominator is on the bottom. And then avoid stacking fractions. It gets hard. So I just proved it to you. It gets hard when you have to stack fractions. So if you're really, really good and comfortable with math, specifically that type of, but if you're not, I don't know what that is. If you're not happy about it, just keep it simple. That is loud. It's getting louder. Okay. Let's do another one. Let's solve for lambda. So if I have E equals HC divided by lambda, what do I do to isolate lambda? Can I leave lambda in the denominator if it's isolated? So even if I had equal to 1 over lambda and had lambda all by itself on one side, it's technically not by itself because it has that math function. It's the reciprocal of it. We don't want it to be the reciprocal of it. I just want lambda by itself. So I need to get lambda out of the bottom. How do I do that? So it's being divided or multiplied by it. It's being divided. So to get rid of it, or move it at least to a numerator, not a denominator, is I need to multiply on both sides. That way, my lambda is no longer in the reciprocal denominator. So I have lambda times E equals HC. So I still want lambda by itself. How do I get rid of the E? Divided by E. And now I have isolated lambda equals HC divided by E. So that one was a little bit more confusing just because lambda, you had to move the lambda to a side that made more sense before you can really do it. So I just want to remind you, like, don't leave it in the reciprocal. Don't leave it in denominator. It needs to be by itself in the numerator. Any question? I know I keep saying that, I'm sorry. Okay, strategies for variables and denominator. That one means that it's in the bottom. So, 2 divided by x. The variable's in the bottom. Multiply both sides by the variable to get it out of the denominator. Take the reciprocal to get it out of the denominator. Turn the other side. Oh, these are different types of ways. Turn the other side into a fraction by dividing 1, cross multiply and divide. Divide by the numerator, remembering to cancel it out as 1. All 4 of these would help you get the right answer, but this is one of the examples of what's best for you. What I just showed you was number A, and that works best for me. But there is no right way to do it as long as the math works out. Let me know if I'm going too fast because I'm going faster than I expected. Oh, okay, let's do another one. This one is under the ideal gas laws. I think this, I don't know if this is Charles's law. Laws that compare gases where you're keeping something constant. So I think this one is, you're keeping the amount constant, but the pressure, volume, and temperature are varied. So it's asking us to solve for second pressure. So we're looking for, let me highlight 2. So we want to get that one by itself. So what do you think is the first thing we do? Oh, I agree. So if I have P1, T1, I'm going to multiply by T2 on both sides. That way it cancels. Oh, this is a 1. And if I multiply by a number, that number goes to the numerator. If I divide, it goes into the denominator. So this one will go in the numerator. And so now I get T, it doesn't really matter the order. It could be 2 times P1 times V1. It doesn't matter. It's all multiplied. So I'll do P1 times V1 times T2 equals P2 V2. What's the next step?
First, your P1, V1, T2 side, that'd be over T1.
Yes, thank you. I knew I skipped a step. Thank you for checking me. Okay, equals P2 V2. Now what? Divide by V2. So that way the V2 cancels. Actually, let me do a different color. Now that we are dividing it by V2, if it's being divided, it goes into the denominator. So I don't know if that's the best kind of saying it goes into the denominator, but dividing it by V2 or multiplying it by 1 over V2, that's the same thing. As long as you know it's going to go in the denominator, not the numerator. So if I wrap all of this up to a different color, P2 will equal, I'm just flipping it just because I want to isolate and have it one side. P1 times V1 times T2 divided by T1 times V2. All messy, but we just got to clean it up in the very end. So just double check and make sure I did that right. All right. See how easy it is to like put the number in the wrong spot. So this one, maybe if you put in the numbers first and then rearrange the numbers, it might be easier. But you still want to be comfortable doing this. All right, this one, similar problem. We're gonna solve for T2. Actually, I think it'd be better to highlight it. Right now, T2 is in the denominator, and we can't leave it in the denominator. Anything we're looking for cannot be in the denominator. So what's gonna be the first thing I do? Two cancels. So I have T2 P1 B1 over T1 equals P2 B2. All right. What do we have to do on the left-hand side? Because I still want T2 by itself.
Multiply by T1.
Absolutely. I like the denominator, so I'm going to get rid of it. So I have T2 times P1 times B1 equals P2 times 2 times T1. Now what? Because I want, let me go back to this. I want to isolate T2.
You divide by both, B1.
Yes, you can divide them one at a time, but since they're both being multiplied, it would be better to like do it all at the same time. So I'm gonna, oh, oops. B1 times B1. That way these two cancel. And now I have T2 all by itself. So T2 equals P2, V2, T1 divided by P1 and V1. Just double check everything looks good. That's probably like the hardest problem you'd ever have to do. I might throw in different types of letters and different types of expressions, different types of variables, but that's probably the most steps you would ever have to do to rearrange. So if you're comfortable with that, you're good with letter math. Now we just gotta practice putting it in numbers. Few more slides. This is the Gibbs free energy equation. Gibbs free energy, forget the definition, but it kind of goes off of like the spontaneity of the reaction. So I think the Gibbs free energy, let me see if I remember my Gen Chem and Gen Chem 2. If Gibbs free energy is a negative value, your reaction is spontaneous. If Gibbs free energy is a positive value, yeah, it might be enthalpy, but I think that's what it is. If Gibbs is negative, spontaneous. If Gibbs is positive, it's non-spontaneous. Delta H represents enthalpy. So the enthalpy of a reaction is energy, kind of gives off or requires. And then T is for temperature and delta S is entropy. So entropy is like the disorder of a reaction. You'll hit this in Gen Chem, but I just love like talking entropy and enthalpy. Entropy is fun because like, let's say if I have a reaction that produces a gas, if I have a liquid, add two liquids together and it produces a gas, there's a lot of disorder. And so you probably have more entropy. So positive entropy is a lot of disorder. Negative entropy would be like less disorder. But you're not gonna be tested on that during this course. That's gonna be Gen Chem 1. But if I needed to ask you how to rearrange this, and I want to get delta S by itself, we can still do it based off what we've been learning. I do not want this. So the first thing to do what?
No, it doesn't have the whole thing.
So even though these are multiplied together, they're just like one unit. So if I was to add both sides, I'll cancel them out. So they're still being multiplied, but it just helps make things a little bit easier. So delta G plus T delta S. That was how we were able to isolate delta H.
Did you say one of those was enthalpy?
Delta H is enthalpy.
Delta.
Yeah, so how much energy a reaction like gives off or requires. So like when you think endothermic or exothermic is a combustion reaction because it gives off so much energy. Endothermic would be something that requires energy. So maybe it usually is a reaction that gets hot. And yeah, it gets like warmer to the touch because it requires, right? I'm pretty sure that's correct. I'm rusty. I think this chemistry is kind of like boring on paper, but in lab, it's so much more fun because you're actually dealing with temperature changes and you're feeling how a reaction changes. And so if like a reaction is cold to the touch, it's typically exothermic because it gives off its energy into its surroundings, whereas endothermic would heat up because it's taking heat and energy as from its surroundings. Yeah. So it's more fun because you can actually like feel it happening. Ooh, sorry, I can definitely like talk about this forever. But I didn't know this until I did some research, but hot hands is just iron. They take iron and they put it into a package and you know, do this to it. But what you're doing here is you're adding oxygen. So you're adding that oxygen, but you're really creating rust. And rust is what's causing that hot hands to heat up. And so that would be an endothermic reaction because it's heating up. Versus a cold pack. If you were to get a first aid kit, and I think I forget what chemicals they put it into, but a great chemical to use is like potassium chloride and water. You mix those two chemicals together, and then once they combine and you do all that, it gets really, really cold to the touch, and that would be an exothermic reaction, that it's colder. So we use those in our everyday life, but when you actually like look into what is causing it, it's like, oh, okay, that makes sense. Yeah, chemistry in my labs that I've written for that lab are like real life examples, and we just analyze real life examples. Okay. What if the variable we want is tied up with more than one operation? We've kind of already done that, especially in like this question here. You have to take it one at a time, break it down. PEDMAS, which would be thinking of order of operations. What is, you know, the first thing we need to do? Hit the parentheses first, or depending on where. So solve an equation, make sure you're doing it in the reverse order of operation if you're trying to isolate what's inside. So if it's inside those parentheses, that'll be the last thing you do. But if it was inside with just numbers, that'd be the first thing you do. Are usually the first thing you're doing when you're solving for a variable, because they're usually the easiest things to move around. So yeah, there's going to be different orders, and I'll show you examples of that throughout this course. Okay, different orders. We want to isolate the T. But let's think about the order of operations. This T is being multiplied by this S. But over here, we have addition, subtraction. So the first thing you need to do to get rid of something is you have to start with the easy ones, so addition and subtraction. So this is confusing. I don't want you to be confused by that. Just leave that negative there. Delta H minus V minus delta S. How do I get rid of this delta H? Subtract. So this is why you might be confused. You think of this negative sign belonging here. It does just by itself. And because there's no number out front, no plus minus, you would subtract by delta H on both sides. So delta G, make sure that order is correct, minus delta H equals negative T delta S. All right. What do you think the next step is?
Divide.
Yes, so here's something where I might add on an additional step. But I'll do it divide by delta S first. So if I divide, I keep doing this, I'm sorry. Divide by delta S. I would get delta G minus delta H over delta S equal minus T. How would I get rid of minus T? Or minus, just the minus.
You have to reverse all buttons. That's fine.
So yeah, so if that negative sign's out front, it's still multiplication. You're assuming it's a 1. So what I would do, I mean, here to get rid of it, you would just divide by -1 on both sides, and that would get rid of the negative sign out front. That's just going back to like all the nitty gritty. But to save that step is I would probably up here color. I would divide by negative delta S because you would have to divide by that negative sign anyway. Does that make sense? Do I need to repeat that or? Okay, so once again, I'll just do it anyway, just because I know my explanations are not always great. If you have a number by itself, you always assume there's a 1 out front, always. So to get rid of a negative out front of a t, that's me saying, okay, it's multiplied by -1. To get rid of the -1, you have to divide by -1 on both sides. So that would work if you broke it up into multiple steps, it would still work, but I tend to, you know, do it all at once. So divide by negative delta S on both sides. And now I have t equals, sorry, actually, I could simplify this one step further. Be like that,
The negative not distributed to the.
it would distribute. Yeah.
H.
If you left this like this, you'd be correct, 100%. It also distributes here. So I'm just doing the simplest, I feel like I'm going back to like high school and I'm like, what is the simplest method? What is the simplest way? That would be negative delta G plus delta H. Delta S. So it has to distribute. It does because algebra would expect it to be. It just, yeah.
And that's the same as saying it's negative, like. Fraction.
Yes, you want it to be like this. If you left this as is and then had that negative out front, it would be the same thing.
A negative AG plus, or not, delta G plus delta H over delta S.
Sorry,
Like that
I
whole
agree with
fraction-
you.
That whole fraction, basically.
The whole thing would be negative, yes. One more slide and we'll move on. Okay, so this one is gonna be if you take general chemistry too. If you're taking engineering, I think you might do a little equilibrium in engineering. I haven't taught engineering chemistry, I just do the labs. But this isn't a great example of an equilibrium calculation. So if you're taking Gen Chem 1 and Gen Chem 2, you won't see this until Gen Chem 2. But we still have variables. K is the equilibrium constant. And then NO2 inside brackets represents the concentration of this particular chemical, squared, and then into O4. So this one's saying solve for specifically the concentration of NO2. So we want to isolate NO2. If you're more comfortable like rewriting this and like putting a letter in and just saying K equals X squared over Y, same thing. You just gotta figure out and like, you know, do what works best for you. When you hit Gen Chem 2, you'll definitely be seeing a lot of examples looking like this. The first thing we wanna do, because I know this can seem confusing, is we need to get rid of this one on the bottom. By 204. Just assume this is all one variable. So that's why I renamed it letter Y. If I do that, I now get K into O4 equals NO2 squared. All right, who remembers how to get rid of the square? Yes, to get rid of a square, you have to do the opposite on both sides. The opposite of a square root is, of a squared is a square root. So, I will point out that square root is the same thing as multiplying being to the 1/2 power. So if you have your calculator in front of you, definitely locate your squared. Usually you have to press second and then square root. But if you are more confident in using the exponents, you can also use the x with a box next to it. And that one you can put 1/2, 0.5 in there. So both things has to calculate it with numbers. So yeah, that's the same thing. All right, so to get rid of that, you square root both sides. And so now we have NO2 equals the square root of K minus 4. Great job. And that's it. So. And that's the last slide I have on this. Are there any questions? All right, so right now, let us get out our activity. If you are online, I did publish activity before coming in. We're gonna practice doing letter math. We'll do it. I mean, we only have 4 more minutes until the break starts, but you could do it throughout the break, or I'll just give an extended break. So maybe give you 10 minutes instead of 5, and then do your best to work through some of the problems. And if you want to know the answers, they're on the bottom of the back page. Okay, let us move on. If you have any questions, remember that the answers are on the back of that page. If there was anything you were really confused by, I'd love to work after class. Unfortunately, the unit conversions I think it might take me more time, so I don't want to use up some class time on that. But I am here after class to help any of those that are really confusing. Let's move on to unit conversions. I do want to point out, if you've looked at the homework I did for 1.3 dimensional analysis, it definitely requires some unit conversions. So I think I might combine this section with those questions so you don't have to redo most of them. I might add a few more to a new section, but it won't be as intense as that section. So that one will just count for unit conversions. But yeah. So chapter 2, section 2, if you want more practice, which practice always helps, especially if you are needing the practice. There are lots of examples worked out in the textbook, along with like at the end of the chapter questions. Those are great resources, and the answers are provided. I believe the odd questions are in the back of the book. But yeah, highly recommend practicing to get yourself more and more comfortable. Let's complete this table. Why are there multiple possible units for each measurement? When I think of grams, kilograms, pounds, ounces, what do they measure? Weight. I think chemistry, we call it mass, but weight and it's absolutely correct. So I'm gonna do weight and mass. So it's weight. I just know chemistry wise, mass is the more correct, but weight is also correct. When I think miles, inches, meters, and centimeters, what do you think of? Distance. When I think of like a centimeter, I don't think distance, I think length, but I think distance is absolutely 100% correct. So I'm just gonna add length in there just for like the smaller ones, like millimeters. Days, years, seconds, minutes, hours. Time, definitely. Liters, milliliters, quarts, gallons. Volume, yes. Can anyone give me a good reason why we have different units? Like, I'm not gonna say like, just can anyone give me a reason why? Metric system, yeah. Depends on where you are in the world. So like if you're born in Europe or Asia, you probably would be very used to saying maps and kilometers. And when you're we tend to use miles. So that would be a very big, obvious like between the two. Sometimes also we have to go between units because if I was to say like go a kilometer, I wouldn't want to use it in centimeters. I would want to say like go 10,000 centimeters. I don't know if that's correct, but pretty sure that's correct. I'm not 100% sure. So we do play around with units when we want to be more reasonable with our measurements. I know if you're a baker like myself, I love to bake, so we tend to use cups, not gallons, but cups. We use teaspoons, tablespoons, things like that to help make baking easier versus it'd be harder to say, okay, measure out 0.25 gallons or pints. Like it'd be more difficult for us to do that. So we will sometimes go between already done unit conversions in sometimes, because I know sometimes I'm like, well, how do I go between grams and ounces? Like I know there are 16 ounces in a pound, or I don't have cups in the bags. I know 8 ounces is equivalent to a cup if it's a liquid. So we've already used these conversions in our heads. We've done millimeters, centimeters to meters, things like that. So there are multiple possible reasons why we would do that. Also as an American, we tend to have our degrees in Fahrenheit. So if we were to do temperature, whereas in chemistry or in science, or if I was to leave America, they would switch to Celsius. So it's hard to do that conversion, I'll be honest with you. But we tend to have to do these conversions because of where we're at in the world. We're gonna kind of review dimensional analysis because you've already been doing this math before, but now we're just gonna introduce different types of unit conversions. Always start with given. I think when we were doing this section, I would point out what do we want and what are we given. Always start with what you're given, and you can assume that that's the number over 1 if you were to do the full fraction. And then you want to make sure you have your unit conversion or equivalents. If they're not provided for you, now I'll say now, this will not be provided for you because you want to be comfortable understanding that there are 1,000 milliliters and 1 liters. So as you do it more and more and more, you'll be expected to have it memorized. Multiply by the conversion factor set up as a fraction. So the fraction cancels out the units of the given. We're trying to get rid of the given and go with what we want. And then some conversions require more than 1 conversion factor. If you have done my 1.3 homework, then you would have seen that a lot of those conversions required multiple ones. So it's great practice. Stringing together the conversion factors to connect what you are given with what you want to find. So that was the gist of dimension analysis with conversion factors. So here's a great example of I'm not going to provide this conversion factor for you. If you don't know how to do equivalence in yet, I like to write it out like this. Okay, I have minutes, that's my given. Convert 7.5 minutes to seconds, that's my want. So I need to figure out an equivalent between minutes and seconds. So if I have 1 minute, the bigger of the two, 60. So, sorry. If you don't enjoy doing this in your head, I would first start off by writing out my equivalents or my unit conversion in front of me. So I know, okay, I know there are 1 minute, for every 1 minute, there are 60 seconds. So I'm going to come down here and I'm going to start with what I'm given, 7.5. Ooh, let's check that. Sorry, I haven't done the math yet. I'll do it with you, but I'm pretty sure you're right. All right, so I have 7.5 minutes. I want what unit in the numerator? You want the want in the numerator. You want the given in the denominator. So I want seconds in the numerator and minutes in the denominator. So that'll be 60 seconds for 1 minute. So I'm using this converter. So 7.5 times 60. Yeah, 450, you're right. Oh, that works too. I like that. So if your mind works like that with these types of conversions, that would work. Sometimes when you get into hard conversions, like I think torr to atmospheres, the types of pressures, there's like 705.63 torrs for 1. When it gets more complicated, definitely use your calculator. But when the math is quite simple like this, your brain, whatever works for your brain is whatever works. That's awesome. I could do that in my head, but I don't trust my brain. Great job. So sometimes I think I have done this in the past where like in the homework where I said, okay, well, if I have 10 hours, how many seconds is it? If I have 1 hour, how many seconds is it? That's when you want to incorporate the additional conversion factors, but these are just some more straightforward, just one conversion. 7.2 minutes. So if I had 7.2 minutes. (7.2) times 60, I get 32. Good questions. Just make sure that you type in your calculator 7.2 times 60. Now, hours. We already have that minutes to seconds conversion, so that's 1 minute equals 60 seconds. If I have 1 hour, how many minutes? 60. So our given is 24 hours, our want is seconds. So I need to start off with my 24.0. Is zero significant?
Oh, yes.
Yes, that is a significant figure. So this is a case where I want my answer to have 3 sig figs because they give me 3. Back here, they give us 2 sig figs. Did we write our answer in 2 sig figs? Yes, we did. Yay, we did it naturally. Okay. Okay. So 24 hours. And I want my 1 on top, my given on the bottom, so I'll do 1 hour here. I can't do seconds. I cannot do seconds just yet because I don't have an equivalent here that goes from hour to seconds. If you want to be extra, you could, but I just don't want to. Yes. Okay, so now my hours cancel. I have minutes. What's the next step? I now need to convert from minutes seconds, so I want my 1 on top, so 60 seconds for 1 minute. And now my minutes will cancel, and my overall units are seconds, which is so 86400 seconds. Is this written to 3 sig figs?
Yes.
It comes naturally, but sometimes it never hurts to double check. The good news is for your exam, you're going to be given multiple choice questions and the sig figs are going to be already there. Unless it's like, write it to the correct number of sig figs. That would be the exception to the rule, but typically if it was a question like this, your answer would be there and it would be very obvious which one the answer is, and it would already have the right sig figs. If you're getting the answers wrong on homework, sometimes it doesn't hurt to just check and make sure you have the right sig figs. Ooh, one more step. Okay. Convert 22.3 days to seconds. So I'll rewrite what we had before. We have 1 minute equals 60 seconds. And I'm going to shorthand it. I'm going to use S for seconds because that's typically the metric unit for the variable. Sorry. What is it called? I don't know. For one, say it again? SI unit, yes, yeah. 1 hour equals 60 minutes. And then how many hours are 4? I know I'm being redundant, I'm sorry. Now let's put it all together. We are given 22.3 days. So I'm gonna set this up and just make sure that you're putting all of your wants in the top, and in the bottom, you put the givens. But this one's a 3-step conversion, so let's start with the first conversion, one day to hours. And now our day cancels. And then 60 minutes, 1 hour. And now our hour cancels. And then 6 to this. For 1 minute. And our minutes cancel. So I want you to get in the habit of kind of doing your conversions all out like this. You can absolutely break it up. You can do, this, and then underneath it, do this, and then underneath it, do this. But this is what Dr. Patterson was mentioning on a previous slide of you can save time by doing it all out in a giant row of conversions. And then you could type it into your calculator all at once. If you just struggle doing this, you could definitely do this part, press enter, and then underneath it, do, this part, enter, and then underneath that. It's just, we're trying to practice being a little bit more efficient. And so my recommendation is just write out your conversion all the way out, and it'll save you some time. So let me do some math real quick. So that'll be 22.3 times 24 times 60 times 6. I'm not including the ones because they're all in the denominator and it doesn't matter. So you could include those ones by doing all of the top multiplied and then all of the bottom, but all bottom ones. So 926,720. How many sig figs are in the answer? Sorry, how many sig figs are in the question? So I want my decimal place or my answer to end here. So that would be 19, what number? 3. 1, 2. If you want to go on, you can do this in scientific notation. 1.93 times 10 to the what number? Six. 1, 2, 3, 4, 5, 6, 6. Yeah, so both would work. These answers are equal and they're both written to the same 3 sig figs. Oh my gosh, Dr. Patterson. Let's add one more step. Let's convert years to seconds, and let's not be extra. Let's do a regular year, not a leap year, or the average of that would be 365.25. No, let's do a regular normal year. So I have 1 minute equals 60 seconds. I have 60, 1 hour. 1 day equals 24 hours. And I have 1 year equals 365 days. Let's put it all together. I have 4 years. All right, I want to put days up top, 365 days divided by, 1 year. And I want to do 24 hours divided by 1 day. 60 minutes, no, 24. No, I did, yeah. Whew. Now, let's make sure our units cancel out. Our years cancel. Our day cancel. Our hours cancel. our minutes cancel, and then our answer should be in seconds. So 4 times 365 times 24 times 60 times 60. So 126144000. How many sig figs does it need to be to?
2.
2, right there. So I can write the answer as 1, what number do I put next? 1, 3, 1, 1, 0, 0, 0, 0, 0, 0, 0. 2, 4, 1.3, 5, 6, 7, 8 times 10 to the 8th seconds. Both answers are right. So I got 130 million seconds and 40. It's crazy, like, if you go between a million and a billion, how big of a number jump that is. Like, I think a million seconds is like a year, a little over a year, but a billion seconds, like 31 years. It's huge, big amount of difference between a million and a billion. Like showing the progression of doing it all at once to save time, once you have all of those equivalents.
So why is that 130 million considered like accurate if it's almost 4 million more than the actual?
That's such a good question. You're only as accurate as your measuring device. If your measuring device can only measure to a specific unit, then that is accurate. I know it seems redundant. You want to have as many decimals as possible to be accurate, but it's not. If your scale only measures to 2 decimal places, and if you do math and you're getting it to 6, but your scale can only measure to 2 decimal places. So you need to write it in the correct amount of significant figures as to what your most accurate measuring device is. That's for the lab science. We're mimicking lab science here by getting the practice in. I know
So like this example.
this
4
example,
years, Don't be that.
like this
Say,
will definitely be the most accurate when it comes to this example, but we want to get the practice in on, you know, what are we going to do? Or just using the correct rules of significant figures. So I do agree with you. It seems like that's just ridiculous, but, yeah, that's just how it goes. Let's talk about metric. We have SI and we have, translator, but this one is just the metric prefixes. There are some that you're gonna see so many times that it's already memorized. So I think those are the most popular ones. It's going between milli and the normal. I think that's the one. So if I was to go between milliliters and liters, I know if I see milli, I know that there are 1,000 milliliters. And 1 liter, there are 1,000 millimeters and 1 meter, things like that. There are 1,000, I don't know 1,000 millipounds in a pound, if you have to go into that sense. But when I think milli, I also want you to think small. Centi, so centimeter, there are 100 centimeters in 1 meter. Micro, when you get into unit conversions, it's also a very popular one that we use. There are 1 million. Let me do that one in a different color. Let's do liters, microliters and 1 liter. So micro is million. But it's not a big number. It's a very, very small number. It's just saying there are 1 million of these small ones in this. Nano is even smaller. There are 1 billion nanoliters in 1 liter, or nanometers in 1 meter. Pico is probably the smallest you'll see. I know you can go to femto, you can go even smaller than that, but we're not in this class. But pico, 10 to the 12th, that would be 1 trillion, I believe. There are 1 trillion of something. But there are certain ones that you'll see over and over again, you'll get more comfortable with. If you're doing something in Your homework that requires you to bring up this slide, no worries, have it with you, it's a great resource. If you want to go bigger, like kilo, if I want to have a kilogram, that means that it's a very big, it means that there are 1,000 meters and grams and 1 kilogram. Deci is a little bit smaller. Kilo, mega is there's 1,000,000 meters in a kilometer, no, in a megameter. Giga is even bigger, 1 billion, and tera would be the biggest, like a terabyte. There would be 1,000,000,000,000 terabytes, no, 1,000,000,000,000 bytes in a terabyte. I'm sorry, I'm getting like myself messed up. But yeah, these are really fun to mess around with. I do want to point this out because this tends to confuse students. I'll show you how to use these conversions without getting confused, but this just shows you how many. Okay. So we need to do equivalents with these metric prefixes. So start with the 1 prefix unit, assign it to one of them. If you prefer scientific notation, you are welcome to use scientific. I tend to use scientific notation when I'm dealing with a really, really big or really, really small. 1,000, I don't mind having 3 zeros, but I don't more than that. So if you want to say like 1 times 10 to the 3 is equivalent to, 1 times 10 to the 3 grams is equivalent to 1 kilogram, that's the same thing as me writing 1,000. So 1, 2, 3, it's still 1,000. So those are equivalent. So, and I will definitely be replacing it with meters, liters, anything I can replace it with. Moles, anything you think of. Pounds, it doesn't matter. We're gonna write the equivalence between the base units and let's do milliliters. The base unit of a volume is 1 liter. So how many milliliters are in 1 liter?
1,000.
I have 1,000 milliliters in 1 liter. Let me see one. Okay. This one can also be written as, if I go back here, we're having milli and they have a 10 to the minus 3 here. This is kind of like what I want to hit on. This is the same thing as me writing 10 to the minus 3 liters is equal to 1 milliliter. So this, sorry, I'm going to go back 2 slides. This is assigned to the base unit. What students will do is they'll tend to put this here, and that's not accurate. I just prefer to always do it like this. What you might prefer, and we could both be right. You just got to pick what's best for you. I like it like this. Let's go to nano. Nano is a very, very small unit. Okay, so I'm going to do 10 to the 9 nanometers is equal to 1 meter. Same as 10 to the minus, actually, I'll just keep it in the same, go back here. Same order. So I'll be 1 milliliter. 10 to the minus. Same as 1 nanometer. It's 10 to the minus 9 meters. And then centimeter, we've seen more, that would be, how many centimeters in a meter? 100. So when you do these equivalents, whatever works for you, just don't think that these, like these negatives and these bigger numbers, those belong in front of the base one. But I'm really simple and I don't like messing with that, so I prefer to use this method. Any questions on that? I'm gonna prove to you now how you're able to do this. So isn't there another way to write the equivalence? I kind of just showed you here how you can write it in the other way, but I want to prove to you why it works. So I'm gonna do these conversions real quick. If I have 1 liter equals 1,000, I have and if you want to be a little extra, I'm not gonna recommend this, but if I wanted to leave that 1 in front of liter, that's 10 to the 3. That's not me being extra, they just showed you that. That's scientific notation. Okay. These are all equivalents that are accurate. If I was to start with 3 liters and try to switch it to milliliters, I would use my equivalent. I'm gonna start with the first one. I want my 1,000 milliliters on top and my 1 liter on the bottom, and that would give me 3,000 milliliters. If I have 3,000 milliliters, I'm just gonna go back to liters. I want you to practice typing this in your calculator. I would have to multiply it by that conversion of 10 to the minus 3. Remember, if you're typing 10 to the minus 3, that's the same thing as me typing 1e minus 3 or 10 caret minus 3. Don't do 10e minus, that would not be correct. It's 1e minus 3. And that should give you 3 liters. Did y'all get that? Okay, I'm gonna show you where students mess up all the time. They flip-flop. Students will flip-flop these numbers. They will put 10 to the minus 3 here. And I want you to put that in your calculator. If you have 3,000 milliliters divided by 1e minus 3, what do you get?
3,000 divided by,
Divided by 1e minus 3. Yes. Does that make sense? If I had 3,000 milliliters, does it make sense for it to be 3 million liters? No, but because it's kind of tend to be like, my calculator gave me the number, it has to be right. But they always will make this, they'll flip this. So that's why I'm a big fan of doing it like this. I know that there are a lot of milliliters in 1 liter, so I can't mess this up. But if you do prefer this method, just make sure you have that -3 in the right location. And if you want to use this one, I can go back and just do 3 liters times 1 times 10 to the 3 milliliters over liters, and that's what gives you 3,000. That just proves all of these conversions will work as long as your equivalents are correct. I'm gonna fix this because this is wrong. Wrong. There we go. Let's move on. Convert this number nanometers to meters. So always start with the given. So I'm gonna do 632.8 nanometers. Is nanometers a small or a big value? Very, very, very small. So I should be going from a very, very small number to a bigger number. I should be getting a very small number. So I want my meters on the top and I want my nanometers on the bottom. How many nanometers are in 1 meter? A billion. So that would be 10 to the 9 or 1 times 10 to the 9. Both are the same. I'm writing it all backwards. Let me fix this. On the right, I just have that other one if you prefer that unit conversion. I'm gonna do this math with my preferred method, but that's the other one if you like that one. So I need to put 10, or no, meters on top. So I need to put 1 meter on the top and 10 to the 9, or 1 times 10 to the 9 on the bottom. And this one should give me, I'll do this one in my head because I can do that. 6.328 minus 7. Tell me if let's see if I can do this in my head.
It says 6.328 times 10 to the 11.
10 to the 11? Let me double check.
Then you move in the decimal place. The other way. That way where.
Yeah.
Sitting in that.
1, 2, 3, 4, 5, 6, 7. So I got it to the 7th. If you're getting it, so what did you type into your calculator? Can you read it to me?
232.8 divided by 1 e to the negative.
Ooh, that's where you went wrong.
Or
Positive 9. Did you put negative?
Positive.
Positive, and you're still getting 11?
Well, I did 6.32.8 times 1.
That's where, okay, so the decimal place is behind the 2.
you pretty much did the same thing, just.
Well, yeah, so make sure you're doing 632.8 and then divide that by 1e9. So if you put a negative 9 here, that is definitely a common error I see. This one should be a 9. If you get a negative 9, you're getting a very big number. And it shouldn't be big because there's a lot of nanometers in a meter, not a lot of meters in a nanometer. So this one is, there are a billion, big number, nanometers in 1 meter. If you prefer to have that negative 9 in it, you'd put the negative 9 on the top, not the bottom. Yeah, no, this is a great way for us to catch mistakes and make sure it's easier and smoother. Does everyone have the right answer now? Awesome. Does everyone understand why I put on the bottom? I want to get those nanometers canceled, not the, and there are a billion nanometers in 1 meter.
So when I typed it in with a positive 9, it just spit out like the actual decimal.
Yeah, like 0.00.
Yeah, that one you're gonna have to do in your head, but you could also just write it all out. You're right either way. If you don't do it in scientific notation, you were also right. Now, I made sure I had it to the same amount of sig figs as the initial question. So my calculator did not give me the correct sig figs. I think there's also a button for you to convert to scientific notation, or maybe I'm just thinking something else. No. I'm thinking back to high school.
There is a purpose, but it.
Yeah, I don't know if it goes to scientific notation. Let me try. No, okay. I'm making it too complicated. Let's just, yeah, use our skills. All right, so number sense check. This is gonna be very important for us to have the sense about what our equations are, because this is how we can fix our mistakes. If we know that centimeters are smaller than meters and I have only like 2 centimeters, I shouldn't be getting 200 meters. That would just tell me, okay, I made a math error. And I do this all the time. I type things in wrong or I just go too fast. But I use my sense check to say, okay, let me go back and check my numbers. So that's gonna be very, very important when you're doing this. Don't just blindly accept. I know in your homework you get unlimited, but you don't get unlimited on the exam. I'm so sorry. I know why, it's not fair. But that's gonna be very helpful to kind of make sense of things. So ask yourself if the numbers make sense. Let's go backwards now. I have 4.2 times 10 to the minus 6 meters to nanometers. So I will write up the conversion again. So it would be 10 to the 9, or 1 times 10 to the 9 nanometers. There are 1 billion nanometers. They're very, very small. So there's a lot of them in a meter. Or 1 nanometer equals 10 to the minus 9 meters. Just remember, this would go in front of the base unit, not the so start with what I'm given, 4.2 times 6 meters times, I want 1 meter in the bottom. And I want my big number in the top, because there's a lot of nanometers in 1 meter. 1 meters cancel. So what is 4.2 times 10 to the minus 6 times 1 billion? So I'd probably be moving it over. I can't do this with math. I don't trust myself. I'm sure I could, but I don't want to.
So we wouldn't put 4.2 E minus 6. We would.
You would. You would do 4.2 E minus 6 times 1 E 9.
Yeah.
And I got 4,200 nanometers. Y'all got that?
Yes.
Are my sig figs correct?
Yes.
So my timer just went out, so that's the end of today's class. I need to see if the rest of it's practice. No, okay. Let me double check. We'll do the rest of this next class, because it should take like 2 minutes. And then we'll do verse and then the 1.7. But yeah, have a great weekend, and I will see you on Monday.